Well, thank you for being here this afternoon. Today I'm going to present an overview of the role of euendoliths in carbonates. And first I will explain what are euendolithic microorganisms, as probably most of you don't know. And then I will explain a little bit what is their role in carbonate precipitation, but I will mainly focus on their role in carbonate dissolution. So far we've been talking about carbonate formation, and I'm going to show you that that can dissolve as well. So first, what are the euendoliths? They are actually the true borers which penetrate actively into substrates here and leave specific galleries, in comparison to what we call chiasmo and cryptoendolithic microorganisms, which are taking advantage of the natural porosity in substrates, and in comparison to what are called epilithic organisms growing at the surface of substrates. And those borers are comprising three different groups: cyanobacteria, algae, green and red, and fungi. And they are mostly filamentous, although you can find some cellular organisms, and their diameter, the filament diameter, is comprised between 1 and 30 microns on average. Their diversity is poorly known, actually, even though it was studied since decades, and that's probably mainly due to the fact that identification, either way, of the boring traces or the filament themselves were based on morphological criteria. But since the development of molecular tools, we are now discovering more and more new species, and that's especially true for the green alga Ostrobium that you will see later is the main agent of carbonate dissolution in carbonate systems. And we thought up to recently that this alga this genus comprised only 1 or 3 different species, and now we're up to probably 16 new species. These organisms are known since the Mesoproterozoic, which is about 1.6 billion years. And the first trace was of a cyanobacterium found in stromatolites in China. And here is probably what is probably the modern counterpart of that cyanobacterium that we believe is Hyela balani, which is a common cyanobacteria found in coastal environment. So those organisms have been known to play a major role in carbonate formation and dissolution since geological times. Problem is that usually they are overlooked. So let's see what is their role in carbonate precipitation with the process of micritization, and a special case with the stromatolite formation, and thanks to the previous speaker, because that's really nicely tied together. Well, in the 70s, Kolbluk and Risk realized an experiment with Iceland spar to get the colonization of by natural communities of euendoliths and see what was going on at the surface. And those endoliths were entering into the Iceland spar crystals, and they were euendolithic, but they were also partly epilithic, sticking out of the substrate. And because of their metabolic activity, photosynthesis, they were creating conditions at the surface of the substrate which would allow the precipitation of calcium carbonate and form micrete envelopes. Here is a picture to show you how the precipitation can occur around a filament. And these authors suggested that this process was involved in sand preservation and reef cementation. So again, this micritization is occurring at the surface of the substrate. Later, people showed that this micritization process could occur inside the boring traces of euendoliths after the organisms vacated the borings. Of course, they would not bury themselves. It doesn't make any sense. So they would vacate their gallery and leave some space, and they would be precipitates such as aragonite inside those boring traces. And here is an example of a sand grain fully colonized by euendoliths. And this experiment was carried out in Bahamas in 2000. They also, Norfdorf et al. Also showed that micritization, this micritization process could take place in living corals. The galleries of boring organisms would be filled with calcite, for instance. They also found some precipitates such as high magnesium calcite around the filament, not inside the gallery this time. And even brucite was also observed around, precipitating around those filaments due to their metabolic activity. And here it was suggested that these organisms were playing a role in coral remineralization, probably the early diagenesis process. And their borings are also very useful as they are well preserved and can be used in paleo reconstruction. For instance, reconstruction of bathymetric levels in the past. So let's see the special case of stromatolites, and that's pretty much the same picture as you've just seen before. Those are modern subtile stromatolites from the Bahamas. They are mostly made by mats of Schizotrix, which is a cyanobacteria, and by entrapping sand inside, they are growing structure, but they are soft at the start, and then they're lithified. Well, as they accumulate, Schizotrix accumulate sand, and new species of cyanobacteria and bacteria are also accumulated, as well as euendoliths. But how do they get there? Well, here's a diagram from Hoffman showing the accumulation of the stromatolite structure. They get buried, there is sediment accumulation, and the Schizotrix filaments are growing upward to keep getting some light and nutrients. So the soft part or the live filaments of the Schizotrix are located actually at the surface here. And as sand is entrapped, well, the sand grains are initially colonized by euendoliths, and the euendoliths, which are able to grow on rolling sand on the bottom or resuspended sand, are very specific, and this is the Hyela and the Cyanosuchus. And once the sand grains get entrapped in the stromatolite, the sand grains get more stabilized, and there is a shift in community of euendoliths and a dominance of the cyanobacteria called cyanobacterium called Solensia sanguinea. Sorry. Then the lithification process starts, and this is due to the degradation of extracellular polymeric substances, which are mainly produced by Schizotrix and Solensia. In the case of Schizotrix, it's production of organic matter which will be degraded by bacteria. And in the case of Solensia, they are growing from one grain to another grain, and when they get outside of one sand grain, then they become crypto or chiasmo-endolithic, and then they enter again a sand grain and become again euendolithic. But the outside part is actually creating the conditions for the formation of micritic layers, and that's how they accumulate, and that's how lithification is taking place as well. Well, I'm probably speaking too fast. Now let's see the dissolution process, which is due to these organisms. All kind of carbonate substrates from all kind of ecosystems, freshwater, marine, terrestrial, even terrestrial ecosystems are concerned by euendolithic dissolution, carbonate dissolution. And it goes from sand grains, shells, limestone corals, living corals and dead corals, foraminifera, etc. You can see on this picture, which is a live living coral which was collected in New Caledonia, the green band that those organisms would form, or here also on this acropora. Well, what is the mechanisms involved in this carbonate dissolution? Is it a purely chemical process due to the water chemistry with low pH and a saturation state of carbonate minerals below 1? Or is it due to a bacterial activity which remineralize organic matter and create the conditions which are favorable to dissolution? Probably not, because this dissolution would be random and you would not see those galleries which are really conforming the shape of the filaments. So there must be, and plus this dissolution occurs in supersaturated waters, such as in coral reefs, where you have a saturation set about 3 or 3.5, depending on the ecosystem. So there might be an active biogenic dissolution, but how does that work? Well, several hypotheses were given since the 70s, and they all agree that there is a front of dissolution at the apical cell of the filament getting inside the substrate. It could result from the production of an acid, and that's probably the case of fungi, which are organotrophic organisms. And as for phototrophs, it was hypothesized that dissolution would take place during the night when respiration is going on, or due to active transport of protons, for instance. Well, Garcia Pichel made a nice review in 2006 and hypothesized different processes for cyanobacteria, euendolithic cyanobacteria. First, he suggested that there might be a temporal separation between photosynthesis and respiration, confirming that during respiration at night there might be dissolution going on because of the CO2 production. Or there is a geographical separation by day. Photosynthesis might be going on near the surface of the substrate, and at the apical cell would be briefing and creating the condition for carbonate dissolution. And then he suggested the presence of calcium pumps, which need ATP energy to be functional. Well, it took 4 years for Garcia Pichel et al. To show for the cyanobacterium Mastigocoleus testarum maintained in culture that there is no geographical separation of the process. And here, along a filament of the cyanobacterium, they studied the photosynthetic activity and showed that there was no significant differences along the filament. Photosynthesis is taking place everywhere, not just near the surface. Then, to show that it's related to calcium pump, he measured the release of calcium in the medium. From here is the substrate, and the green are the filaments of the cyanobacterium, Mastigocoleus. When the lights were on, there was release of calcium in the medium, and when they were turned off, it took 2 hours to stop the process. And then when they were turning the lights on again, the calcium release was taking place again and was even higher than before the dark phase. And remember that. So they really suggested that calcium pumps were involved in this dissolution process, and it would occur during light because these transporters need ATP, so they need the photosynthetic activity to be run. But this type of measurement of calcium release is a proxy of dissolution. They didn't run any experiment by night. We don't know if there is dissolution going on by night without release of calcium. And this is true for only one strain, which is Mastigocoleus testarum, maintained in culture. So we wanted to see if we could measure the same things pretty much and highlight more the process in natural communities under light and dark. So we carried out 3 different experiments. I'm not going to go too much in detail, but I'm hoping to give you enough information so you understand what we did. Well, we ran an experiment in an indoor flume in Hawaii where we had constant light and natural water chemistry. We didn't change the water chemistry to measure by day and by night dissolution and photosynthesis respiration of euendolites, colonizing either way natural rubble, like here, which are coral debris that you can find on a coral reef, or coral blocks which were colonized by euendolites for a while to get mature communities dominated by the green alga Ostrobium. We'll also run an outdoor flume experiment in Hawaii, which is here, to measure photosynthesis under natural light cycle and let the pH go up along the day and see if we could still measure dissolution at really high pHs and saturation state of aragonite, because here we are dealing with corals made of aragonite. And finally, we did a tank experiment in New Caledonia where we both control light and the saturation state of aragonite of the water. So we realized an ocean acidification experiment to see what was going on. What we did measure here is the total alkalinity and the pH of the seawater to measure net dissolution or net calcification, if any calcification was going on. Well, I'm not going to show you all the results, but here what I want to show you is that we had a really nice relationship between net dissolution of carbonates and the net photosynthetic activity of euendoliths here. And that really confirms that dissolution occurs by day and is really related to the photosynthetic activity of those organisms. At the same time, and this is true for blocks and rubble, in the New Caledonia experiment, where we had a dark phase and then a day phase, what we measured here is what we measured here is the dissolution at night was much higher than dissolution by day. So Garcia-Pichel previously was missing the process at night. And it's really important because it's pretty much double or even more than the process during the day. And what we also showed with this experiment is that we had an increase of dissolution by day and by night, which is significant when we decrease the saturation state of aragonite. So ocean acidification would probably stimulate the photosynthetic activity and the dissolution process in the next few years. Now I would like to show you more into details what's probably going on, and this is mostly based on hypothesis at this moment. This diagram was taken from Garcia-Pichel et al. Paper, representing a filament of the cyanobacterium mastigocoleus. And this cyanobacterium is made of cell and cross walls, so it's very difficult, I guess, to transport calcium from one end to another end. It's much more, it's probably easier for Ostreobium, which is the main agent of dissolution in coral reefs, because it's a siphoneous alga. There's no cross walls, so the transfer or transport of ions is probably much faster than for a cyanobacterium. We think that Garcia-Pichel is right, and what he found for cyanobacteria is probably true for chlorophyte here, that there is exchange of calcium ions and protons at the dissolution front, creating the conditions for dissolution, and the calcium is released at the other end during the day. So by day, the photosynthesis is providing ATP, that activates the calcium pump and releases calcium near the surface of the substrate. And we don't know yet which form of carbon is used for the photosynthetic activity of those organisms. Could be directly the CO2 or the bicarbonate ions, but definitely those two forms will increase with ocean acidification. And depending on the condition at the surface of the substrate, if you have a thick boundary layer with a low motion system, you would definitely have reprecipitation of calcium or carbonate calcium at the surface, and that's part of the microtization process that I was talking about earlier. I actually have seen this in my tanks in an outdoor flume one day because the pump which was running the seawater stopped. So the pH was growing up, building up, building up, building up. And instead of having my green blocks looking nicely, I had white blocks, and I had whitening like in the Bahamian waters that you probably heard of. And it was, I thought that everything was dead and I killed everything. And then the next day I put the pump back and they were green again, and probably those precipitates dissolved instantaneously during the night when respiration was going on. It was really cool. At night, what's probably going on is that we have those filaments are respiring, producing CO2 and protons. They are probably exchanged easily here at this end, and dissolution is much higher at night because the pH is going down and it's more thermodynamically favorable to carbonate dissolution. But the calcium pump stops. So where does go the calcium? That's our question. We hypothesized that it's probably accumulated in vesicles because calcium is toxic for cells, but this has to be shown, and it's just an hypothesis at the moment. Now I would like to go from the micro scale to the large scale and give you an idea of the relevance of this process of carbonate dissolution at the ecosystem scale. Well, first of all, euendoliths, I said earlier, are present in all ecosystems, cold, temperate, subtropical, deep, shallow, but they are really significant in tropical systems and play a major role in coral reef functioning. Well, here is a very schematic diagram of a coral reef. And I'm showing you here a live colony of coral where boring microflora would be near the surface, just below the coral tissue. And here is a dead coral colony, and colonization is taking place from outside inside, while here it's probably starting from the substrate of fixation going inside and keep growing with the growth of the coral. So those organisms are colonizing each type of carbonate substrates in coral reefs, including urchins, algae, etc. And they play a role in carbonate dissolution, but they are also important primary producers, so playing a role in carbon cycle and even in the nutrient cycles. And of course, they can be influenced by various factors, such as the biotic factors. One of them, which is a really important factor, is the grazing pressure on those photosynthetic organisms. Human activities such as pollution, sedimentation, and of course global change factors such as ocean acidification that I just showed you. So let's talk about numbers and see how significant is this process at the ecosystem scale. Okay, this is our horrible table. I'm not asking you to remember all the numbers. I just want to show you that different studies were carried out from Australia to the Bahamas, using different type of substrates, mostly coral skeletons, but also sediment, limestone, strombus shells, etc. The methodologies used to estimate the rates of dissolution here are diverse, meaning that most of the studies were based on microscopy measurements, but the latest study that I just showed you was based on alkalinity measurements, and others did also measurements by weight balance, which is not so accurate. But anyway, just remember the blue number and the red number. This blue rate of carbonate dissolution was found for sediment, reef sediment, and it's about 3.65 mole per square meter per year. And here is a table summarizing the rates found for hard substrates in coral reefs. And that's a huge range going from 0.5 to 42 millimole per square meter per day. And that converts into 4 mole per square meter per year on average. And that's a conservative number here. So let's go to the large scale. And coral reef worldwide surface area is about 0.6, 10 to 12 square meter. And you have to know that 80% of a coral reef is made of sand. So if I apply the number found for sand in terms of carbonate dissolution due to euendolites to that percentage, and this number to what's remaining, the hard substrates, we estimate that biogenic dissolution of carbonates by euendolites today at ambient PCO2 is about 2.2, 10 to 12 mole per year. And I just showed you the positive effect of ocean acidification on this process using total alkalinity, but 2 previous studies also showed that the same number based on microscopy measurements, and therefore we estimate by the end of the century this could double. At the same time, you probably know that coral reefs will also less calcify under ocean acidification, due to the reduction of calcification by corals and crustacean algae especially, which are the main reef frame builders. And this number should decrease by about 30%. Therefore, the production of calcium carbonate in reefs should be around 6.3, 10 to 12 mole per year. So in conclusion, today we estimate that about 25% of the carbonate produced in coral reefs is dissolved by euendolites. And it could go up to 80% by the end of the century if ocean acidification, eutrophication, and other factors are stimulating their activity. And that's just talking about dissolution by those microbes. Now, if we consider boring sponges, which are also dissolving calcium carbonate in coral reefs, the bacterial activity in sand, and chemical dissolution of, for instance, high magnesium calcite in reefs, then based on a recent model, we estimate that coral reefs will shift to a net dissolution budget before 2065. So it's really a relevant process. Well, thank you for your attention.